Elon Musk's SpaceX has been awarded by NASA to launch their new Nancy Grace Roman Space Telescope, which will be used to explore dark matter among other things. The launch has been set for October 2026 at the earliest, and SpaceX's Falcon Heavy has been selected as the launch vehicle. But how powerful is this telescope? How does it differ from the legendary telescopes such as the James Webb Space Telescope and the Hubble? Let's all find out in this episode, so stay tuned. The next Space Telescope mission will be launched by Elon Musk's SpaceX, thanks to a contract NASA awarded to the company. According to a press release from the space agency, the Nancy Grace Roman Space Telescope, which has a 2.4-meter diameter, will launch in October 2026. A Falcon Heavy rocket from NASA's Kennedy Space Center in Florida will be used by SpaceX to launch the telescope in accordance with the terms of the contract. According to NASA, the price to launch the mission will likely be in the range of $255 million, including launch services and additional fees. The $10 billion James Webb Telescope mission, which will look for early galaxies and potentially habitable planets, was launched into space in December. The 6.5-meter Webb telescope took 2 weeks to unfold itself in space, but it has already recorded vivid views of new stars and old galaxies. According to NASA, the Roman telescope will be launched into space in less than 5 years to study galaxies, exoplanets, dark energy, and dark matter. Exoplanets are planets that orbit stars outside of our solar system. According to the organization, this will make it easier for scientists to understand the cosmological mysteries. What precisely does the Nancy Grace Roman Space Telescope do? According to NASA, the Nancy Grace Roman Space Telescope is NASA's next infrared space observatory that will try to answer the riddles of dark energy in order to address some of the most important cosmological concerns. The telescope, often referred to as Roman or the Roman Space Telescope, will look for exoplanets and study the physics of far-off stars, in addition to searching for planets outside the solar system. Likewise, the Space Telescope, which is scheduled to launch in 2026 or 2027, has a large field of vision that will enable it to produce never-before-seen huge pictures of the universe, necessary for solving some of the most pressing cosmic puzzles. It is anticipated that the mission will last 5 years. The Lagrange Point 2, which is a stable gravitational intersection of Earth and the Sun and is around 1.5 million kilometers from our planet, will be the position of the Roman Space Telescope. In 2010, the Wide Field Infrared Survey Telescope was unveiled. It wasn't until May 2020 that the Wide Field Infrared Survey Telescope was renamed the Nancy Grace Roman Space Telescope in memory of Nancy Grace Roman, a novel scientist who held the position of NASA's first chief astronomer from 1961 to 1963. On December 26, 2018, Roman, who was 93 years old, passed away. Roman earned the epithet the Mother of Hubble during her lifetime because she constantly pushed for new technologies that would enable astronomers to investigate a larger portion of the cosmos. As a result, the Hubble Space Telescope was launched in 1990. Jim Bridenstine, the former NASA administrator, made the following statement while announcing the new name for JWST in 2020. "It is because of Nancy Grace Roman's leadership and vision that NASA became a pioneer in astrophysics and launched Hubble, the world's most powerful and productive space telescope. JWST, which will replace NASA's Hubble and Webb telescopes, has no better name in my opinion," said Bridenstine. Samson A. Johnson, a postdoctoral fellow at NASA's Jet Propulsion Laboratory, told Space.com that Roman is planned to teach us a great deal about exoplanets and cosmology, but will have the capability to do so much more. Right now, and all the way up to and after its launch, there will be a lot of opportunities for astronomers to propose their own ideas for Roman, and there are many interesting prospects, such as studying stellar mass black holes, exoplanet transit surveys, asteroseismology surveys, and much more, Johnson added. The Jet Propulsion Laboratory, the Infrared Processing and Analysis Center, the Space Telescope Science Institute in Baltimore, and a science team composed of researchers from institutions across the U.S. have all contributed to the development of the Nancy Grace Roman Space Telescope, which has been overseen primarily by NASA's Goddard Space Flight Center. Initial plans for the Roman Space Telescope from 2011 indicated it would have a single instrument and a smaller mirror with a diameter of 4.3 feet. The Science Definition Team and JWST Study Office unveiled the telescope's current and final design in the JWST AFTA 2015 report published in 2015. The Roman Space Telescope will launch weighing 4,166 kilograms and will be carrying a payload weighing 2,191 kg, according to the JWST AFTA Science Definition Team final report. According to NASA, the primary mirror of the Roman Space Telescope is 7.9 feet in diameter, the same size as the Hubble mirror, but it weighs just 410 pounds instead of 2,200 pounds. The Roman Space Telescope's two primary instruments, the Wide Field Instrument and the Coronagraph Instrument, are illuminated by the mirror, which also gives the telescope a 0.281-degree square field of view. Excessive solar light is dispersed by the spacecraft's own barrel-like design. The main objective of the Roman Space Telescope, to study dark energy, will be made possible by the Wide Field Instrument's ability to measure the light from 1 billion galaxies over its 5-year operational period. According to NASA, physicists believe that dark energy makes up about 68% of the universe's total energy matter content, despite the fact that they are not entirely sure what it is. Keeping track of how dark energy's influence has evolved through time might be one solution to this issue. By charting the distribution of matter throughout the cosmos and calculating how the universe has expanded since it was around 500 million years old, or about 4% of its present age, the Wide Field Instrument on board the Roman Space Telescope will aid in this investigation. The Roman Space Telescope may find the first signs of dark energy by measuring the brightness and distances of supernovas, the explosions that happen at the conclusion of stars' lifespan. This will help scientists understand how the effect of this unknown force has changed through time. The search for planets surrounding other stars will be one of the goals of Roman, along with other endeavors like the investigation of far-off supernovas and the inspection of extrasolar objects. What are the differences between the James Webb and Nancy Grace Roman Space Telescopes? Both telescopes are designed to operate in the infrared wavelength region. The JWST, though, has a relatively constrained and in-depth field of vision. On the contrary, a very large area of the sky will be covered by the Nancy Grace Roman. This can be explained by noting that both telescopes have different scientific objectives, and as a result, their coverage must change to meet these requirements. Deep lines of sky vision are what the JWST seeks to retrieve. On the contrary, the Roman will give us the big picture. It will complement other massive galaxy surveys conducted from the ground, such as DESI or the planned Vera Rubin Observatory. What methods will the Nancy Grace Roman Space Telescope use to investigate dark energy? The majority of the Nancy Grace Roman's features will make it an effective tool for researching the properties of dark energy. We will be able to comprehend the impact of dark energy on large cosmological scales, as well as the clustering and evolution of galaxies, thanks to the telescope's extensive coverage of the sky, allowing it to capture a record-setting number of galaxies in its field of view and their distribution in our universe. We can make a reliable prediction of the acoustic peak thanks to the comprehensive map of the galaxies. As a result, it will see galaxies that the existing ground-based telescopes might be missing. In contrast, the Nancy Grace Roman will concentrate on capturing signals in the infrared. The telescope will also look at a lot of supernovae, the same kind of things that initially gave rise to the idea of dark energy and the fast expansion of the universe. Above all, its discoveries about dark energy and the large-scale structure of the universe will supplement those generated by other observatories. How will astronomy be affected by the Nancy Grace Roman Space Telescope? With each new telescope, scientists learn something new about dark energy, the makeup of matter, and the nature of the cosmos. As a result of the fact that this telescope will enable us to obtain an extremely thorough infrared map of the galaxies, they will not only include close galaxies, but also primarily very early galaxies, whose light will have undergone significant redshifts because it traveled a great distance before hitting the Roman mirrors. The Nancy Grace Roman will also cover other intriguing topics in the field, such as exoplanets, providing the most comprehensive list of planetary systems in our galaxy, and other astronomical problems in the infrared that neither the HST nor the JWST can solve due to their limited field of view. Hunting for exoplanets. In two different approaches, Roman will impart knowledge to us about exoplanets. One of its core community surveys to start is made to look for microlensing incidents. Johnson argues that we need Roman's wide field of view to watch for these incredibly unusual events, which are the almost perfect alignment of a foreground item and a background star. The foreground object's mass causes a temporary increase in the brightness of the background star by magnifying the light coming from it and bending space in a way that makes it do so. The presence of planets will be detected by variations in the magnification that they will produce as they orbit the lensing star. According to NASA JPL, the Wide Field Instrument will explore the Milky Way and look for about 2,600 new exoplanets by utilizing tiny amounts of light, bending brought on by the existence of mass. The Roman coronagraph will examine dozens of exoplanets that have previously been found as this device searches for new exoplanets, photographing them and doing spectroscopic observations of light absorption, emission, and other radiation. Exoplanet atmospheres include a variety of elements, and scientists may identify these elements and look for compounds like water and complex organic molecules that may be byproducts of life by observing light as it travels through these atmospheres. Astronomers can currently discover young, bright exoplanets that are about 1 million times fainter than their host stars because to technological advancements. However, many exoplanets are 100 million or more times fainter than their stars. This is especially true for rocky terrestrial planets like Earth or mature gas giants like the solar system's own Jupiter and Saturn. Johnson continues, the coronagraphic instrument on Roman, a technological demonstration of the first space-based adaptive optics, is the second way that Roman will investigate planets. This will be crucial for the ability to image planets directly from space in the future and open the door for the next generation of satellite telescopes to look for biosignatures in 2040. With current laboratory experiments indicating the equipment might be able to identify exoplanets 1 billion times fainter than their home star, the Roman Space Telescope coronagraph equipment will be the first high-performance coronagraph system deployed into space. Roman will therefore serve as a crucial building block for upcoming missions that seek to image and describe terrestrial planets that are 10 billion times fainter than the stars that they orbit. JWST versus Nancy Grace Roman versus Hubble. Even though it makes sense to compare the capabilities of the Hubble, James Webb, and upcoming Nancy Grace Roman Space Telescopes, none of these instruments is meant to completely replace the other. Rather, they are meant to work in tandem. Even though all three instruments use infrared light to observe the universe, they each provide a unique cosmic viewpoint. Roman will have a 20% increase in wavelength coverage over the mission's original plan, covering the visible and infrared spectrum from 0.5 to 2.3 microns. This range, according to NASA, will allow the telescope to work more closely with the Hubble, which sees the universe in ultraviolet to near-infrared light, 0.2 to 1.7 microns, and the JWST, which sees the universe in near-infrared, mid-infrared, and a small amount of visible light from 0.6 to 28 microns. The JWST's gold-coated mirror, which has a diameter of 21 feet, dwarfs the silver-coated mirror of Roman, which is the same size as Hubble's primary reflector. The JWST is 100 times more powerful than Hubble and can see things 100 times fainter than Hubble thanks to its enormous mirror, which is composed of 18 hexagonal segments. This allows it to see further into the cosmos. Since light can only move at a certain speed, the JWST can also look farther into the past than Hubble. Actually, comparing Roman and Webb to Hubble is the most useful comparison. According to Johnson, Webb has a significant edge over Hubble in that it is significantly more sensitive and can identify light sources that are 100 times fainter than Hubble. As a result, Webb serves as a superb Swiss Army knife observatory, one that is incredibly adaptable and capable of seeing a variety of objects, from the first galaxies to directly imaging exoplanets. Despite having a far broader field of view, Roman has sensitivity that is comparable to Hubble's. In comparison to Hubble, Roman can observe an area of the sky in a single point of view that is 100 times greater. Roman can now observe tens of millions of stars in a single image or thousands of galaxies at a time. According to NASA, Roman's infrared vision should also enable the telescope to view the universe as far back as when it was only a little more than 300 million years old. However, NASA claims that Roman's biggest asset is the scope of its field of view. The field of view of Roman's wide field instrument exceeds that of Hubble's widest exposure by a factor of 100. Roman will consequently produce significantly broader images of the universe while matching Hubble's sharp infrared resolution. Roman will image the night sky more than 50 times more than Hubble has since 1990 in its first 5 years of operation. High-resolution ultraviolet observations are something Hubble still has the ability to catch that Roman cannot, proving that even the oldest of these 3 mega-telescopes is not in any way rendered obsolete by its forerunners. Roman will be able to identify objects in its wide-field perspective that Hubble can observe in infrared, and that the JWST can see more clearly and in depth. According to NASA, combining the results from the Roman Space Telescope with those from Hubble and Webb could revolutionize our understanding in a multitude of cosmic pursuits. But what is dark matter and dark energy? Why is NASA trying to find the existence of these? What is dark matter? Scientists have never observed more than 80% of the material that makes up the universe. The behavior of stars, planets, and galaxies just wouldn't make sense without it, thus we can only believe that dark matter exists. Dark matter cannot be seen at all. Since it doesn't emit any light or energy, it cannot be picked up by regular sensors and detectors. According to scientists, the substance it consists of must hold the key to explaining its cryptic nature. Baryons, another term for subatomic particles like protons, neutrons, and electrons, are the building blocks of visible matter, also known as baryonic matter. What dark matter is made of is simply an assumption among scientists. It might be made of baryons or it could be non-baryonic, which implies it could be made of many kinds of particles. The majority of scientists believe that non-baryonic matter makes up dark matter. What is dark energy? The unknown component responsible for our universe's pace of expansion accelerating over time rather than slowing down is known as dark energy. That goes against what one may anticipate for a cosmos that was created in a Big Bang. In the 20th century, astronomers discovered that the universe is expanding. They believed that the expansion might either last forever or, if the cosmos had enough mass and self-gravity, would eventually reverse and result in a big crunch. It has since evolved in early 21st century cosmology. We now perceive the cosmos to be expanding more quickly than it did billions of years ago. What might be accelerating the rate of expansion? Astronomers now occasionally refer to a repulsive force as a potential explanation for it. Most cosmologists thought the cosmos did not have enough mass to trigger a big crunch until the late 1990s. The Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey data in particular seem to show that the universe will continue to expand indefinitely, albeit at a slowing rate as the cosmos's inherent gravity and mass attempted to draw it back.